So let's start with part 5 of arithmetic instructions of 8086. We will specially focus on BCD arithmetic and we will see how it is handled using existing arithmetic instructions of 8086. So considering BCD, right, we have two ways of representing BCDs. So one is the packed representation, other is the unpacked representation. So suppose that I need to represent this number 5693, right, in BCD. So in packed representation, each number will be given a nibble, right, or each number will be represented in 4 bits individually. So in a particular byte, what you can see is two numbers can be packed together or represented together. So that is why it is known as packed BCD representation. So if you have a 4-digit number to be represented, you can represent the entire number in BCD format in 2 bytes. Okay, so that's what is packed representation. Then in unpacked representation of BCD, each number is given a complete byte to be represented. Okay, so even though you need to represent only the numbers from 0 to 9, right, the entire 8 bits is given to one number. So this is unpacked BCD. So packed BCD is much more efficient compared to unpacked BCD. So BCD is actually inefficient compared to the entire binary representation, right? But comparing packed and unpacked, packed BCD is much more better than unpacked BCD. Okay, so we will see how numbers represented in packed or unpacked format can be operated upon using various arithmetic instructions. So before going to that, we need to consider another important flag in the flags register. It is known as the auxiliary flag. Okay, AF or AC, auxiliary carry flag. So it is an indicator of a carry getting passed from a lower nibble to a higher nibble. Okay, suppose that an arithmetic operation like this is happening between two 8-bit registers, right? Then when the corresponding nibbles, lower nibbles are added, and if you can see here that a carry will be generated from here and will be passed to the higher nibble. So that condition will be indicated using AF or AC being set to 1. Okay. So let's see the first instruction that is used to perform BCD arithmetic. It is actually an instruction that will help us to see the result in BCD format, that is DAA, that is decimal adjust AL or the accumulator after addition. So what you need to understand is there is no particular extra instructions for BCD arithmetic. We will use only the instructions available for binary arithmetic like add, sub, etc. And we will adjust the result that we have in BCD encoding so that the result can be processed as BCD. That's what we are going to do. Okay, take the actual binary arithmetic operations, use them over BCD, then adjust the result to get the BCD. That's what we are going to do. So suppose that we are performing addition, right? We need the actual BCD result, right? But we will get a binary result. So in order to convert the binary to BCD format, DAA, okay, decimal adjust AL after addition is used. So here what we are assuming is only 8-bit BCD encoded numbers are used, and they are packed BCD representation. So it means that if we have 8 bits, right, how many digits can be represented in that? We can actually represent 2 digits. Okay, so we are going to consider that. Okay, so this is a particular example. We have 53 represented in BCD format and 29 represented in BCD format. Then upon binary addition, okay, the binary result that we have is this one, 124, but actually we expect 82 in BCD format. So we will see how this DAA will help in conversion. Okay, so let's see the algorithm for that. So what DAA does is it will check the binary result, right? So we have the binary result in AL, right? So this is the binary result. So we have that in AL. So it will first check the lowermost nibble. So we need to check this part. So we know that in order to convert from a binary to BCD representation, we will see if it's a packed format, we will see each nibble, right? And if it is greater than 9, what we will do, we will add 6 to it, then we will propagate the carry to the higher nibble, right? And we will be left with the BCD representation of the individual nibble. Okay, so same thing we are going to do. We are going to identify the pattern in the lowest nibble. So for that we are ANDing the entire 8 bits with 0f. So what will happen, this will be turned as 0, then this pattern we will get, and what we are doing, we are checking whether that pattern is greater than 9. Okay, so if that pattern is greater than 9, right, in this case it is greater than 9, right, what we are having here, we are having 10, right, so it is greater than 9. So what we are going to do, we are going to add 6. Okay, so once 6 is added, what happens is auxiliary flag will be generated. Okay, why auxiliary flag? Because there will be an overflow from here, right? So here we will have 1 1. When we add, right, we will have an overflow from here. So that overflow has to be represented, so that is represented by AF equal to 1. Okay, and we will be left with this one, that is 2, right? So that happens over here, and then we need to check the highest nibble. So for that, F0 is ANDed with this entire binary sequence, so we will get the only upper part. And note that there is an already existing auxiliary flag here, right? So what happens is we will actually have that added over here, and so it is already 7, right? So we will have 8 here. Then that pattern will be ANDed with F0, right, and we will extract this pattern, and it will be checked whether it is greater than 98. So actually it is not. So what happens is nothing will be done, it is left as it is. Okay, so that is how this operates. So in short, what this algorithm does is it will extract the lowest nibble first, check whether the lowest nibble is greater than 9, right, and if it is greater than 9, 6 is added. Then carry flag, actually it is auxiliary flag over here, right? So auxiliary flag will be set if there is an excess overflow, right, on addition with 6. Obviously there will be, right, as it is greater than 9, when you add with 6 there will be an overflow to the higher nibble, so auxiliary flag will be set to 1, right? Then the next chance is for the highest nibble. So when we consider this highest nibble, here we have to extract the pattern of the highest nibble, so we are ANDing with F0. Then again we are checking whether the highest nibble is greater than 9, and if it is greater than 9, we are adding 6 to the highest nibble. Okay, then in case of highest nibble, note that no extra auxiliary flag is present for that. When we have an overflow or carry from the highest nibble, carry flag has to be set. Okay, so this is how it operates. Now we will see addition of 73 and 29, and how the result is binary adjusted, binary coded decimal adjusted. Okay, so this is 73 in BCD format, 7 is over here and 3 is over here, 29, we have 2 here and we have 9 here. Then when we add together using add, the binary result left is 124. Okay, so actually we need 102, that is the actual BCD result expected, right? So this will be 3 plus 9, this will be 12, 1 will be the carry, we will have 9, 10. So 102 is the expected result. So how will we do the adjustment? So we will trace the algorithm as it is, right? So first thing is we will check the lowest nibble, we need to extract the pattern, so lowest nibble will be extracted. So what is the result over here? $12, right? So it is greater than 9, so we need to add 6, so we will be adding 1 1 over here, and as usual we will have an auxiliary flag indicator because of a carry to the highest nibble. So we will get 2 here, we will leave it here. Then we have a 1 over here, so that 1 will be automatically added over here, right? So it is 0 1. Then we will check whether this highermost pattern is greater than 9. Obviously it is greater than 9, so 6 will be added. So when 6 is added, what happens is we will have a 1 0 generated. This entire thing will be set as 0, and we will have 1 carry as carry flag, so that will be kept in carry flag as 1. So this 102 will be represented as 1 in carry flag, 0 in the highest nibble and 2 in the lowest nibble.